Hello everyone. Today I'm going to show you a small circuit that can be called an audible ohmmeter or audible continuity tester. The original idea of this circuit is not mine. It has been published. Similar circuit has been published in EDN magazine some years ago. And I'll show you the link in the description below. And sometimes we need to test continuity of any circuit using a multimeter, and usually the multimeters have a kind of single frequency tone, and you can hear the tone when there is a continuity. But it's a single frequency tone and you don't have any idea what's the value of the resistance. It would be good to have a variation of tone with a very little change in resistance, and this circuit can do that. I have the circuit here, and you can see it's a very small circuit, and this is the uni-junction transistor, and which is used as a relaxation oscillator circuit here, and the very small change in resistance connected across this terminal can give you a change in tone. A programmable uni-junction transistor looks much like any other bipolar junction transistor, but its characteristics are very different. Its symbol is shown here. The terminals are anode, cathode, and gate. It is a 4-layer device. If the anode and the cathode are connected to positive and negative terminal of a battery, no current will flow from anode to cathode. Now consider this anode and gate junction. It is nothing but a PN junction diode. If another voltage source VG is connected between anode and gate, this junction becomes forward biased. Current will start flowing. Next PN junction is already forward biased, so the current will continue to flow from anode to cathode. To determine the characteristics of a programmable uni-junction transistor, or PUT, we can connect a resistor with the second source once the gate is forward biased. Current starts flowing from anode to cathode. As the current increases, the anode voltage initially decreases and then starts to increase. This region, as the behavior, is called the negative resistance region, as the behavior within this region behaves opposite to any normal resistance. Any device which shows a negative resistance can be utilized to make an oscillator easily. For a PUT device, we can set the peak voltage Vp when the anode cathode starts conducting. Using these two resistors, R2 and R1, we can set the voltage Vg, and eta is called the intrinsic ratio, and we can easily set this ratio with these two resistor values. When the anode voltage Va reaches Vp, then the PUT starts conducting, and the conduction happens very fast within this negative resistance region. To make an oscillator using a PUT, we need a capacitor across anode and cathode terminal. After setting Vg with these two resistors, the anode voltage Va starts to increase from 0, and when it reaches Vp, the voltage goes down from Vp to a low voltage called valley voltage, and this is the point where the capacitor is discharged by this PUT device, and in the negative resistance region. Then the cycle begins, reaches Vp, goes down to valley point, and then again starts from value to the VP and then goes to 0. So this cycle repeats and we get our oscillation. So by selecting the resistor and capacitors, we can change the frequency, and the frequency is expressed by this equation here, written here. Now, where can we connect a speaker to hear the audible sound? We cannot connect a 16 ohm speaker across the capacitor. The circuit will be loaded and the oscillation stops. We can connect a higher impedance quartz speaker, but that will change the frequency and the sound will not be much. What we can do, we can tap into it at the cathode in such a way that there will be a very little voltage drop at this terminal. At the cathode terminal, we can place a transistor, and on the collector, we can connect a 16 ohm speaker. We can hear an audible sound now. In place of 2 gate resistors, we can use a potentiometer. Now, the beauty of this circuit is that the frequency depends on R3, C1, and the ratio of R1 and R2. So if we use a low value resistance for the potentiometer, changing a small resistance can give a significant variation in the audible tone. By hearing the tone, we can have an assessment what could be the value of the resistance connected at the probe. As you can see that as any unknown resistor is connected across the probe, you will hear a tone, and as the resistance go higher and higher, the frequency goes lower and lower. Of course, there is a limit of minimum resistance which can generate audible tone. To increase the range, we can use higher resistance potentiometer. Presently, what is shown here at the chart is for 100 ohm potentiometer. For instance, with a potentiometer of 1 kilo ohm in place of 100 ohm, same kind of tone generation is possible from 0 to 800 ohm. The practical circuit is shown here in the photo. This is the unijunction transistor, and this is the transistor to drive the speaker, and this is the 100 ohm potentiometer. I tried to probe the waveform at the capacitor terminal or anode terminal. You can see the waveform here. Capacitors charging and then quick discharge, charging and quick discharge, and the top, the peak is called the VP, that is quite uniform, and this is the valley point. The circuit board, 3.7 volt lithium ion battery, and the speaker, everything is put inside a box. Several resistors were used to find out the performance: 1 ohm, 10 ohm, 22 ohm, 50 ohm, and 120 ohm. This is the unijunction transistor, and this is the transistor driving the speaker, and this is the 100 ohm potentiometer, and the capacitor is connected there, and this is the speaker, 16 ohm speaker, and the power is coming from 3.7 volt lithium ion battery. So I'm closing the circuit inside the box, and after connecting the probe, I'll be trying to measure the resistance. I have 5 different resistors: 1 ohm, 10 ohm, that is 20 ohm, 50 ohm, and 120 ohm. So let us see with the first one. even 1 ohm, you can see the difference in tone. And this is with 120 ohm.